In this video, we'll solve a related rates problem. This is the 3.9 pre-class video. Let's look at this problem statement. Two cars start moving from the same point. One travels south at 50 miles per hour, and the other travels west at 40 miles per hour. At what rate is the distance between the cars increasing 4 hours later? Alright, to tackle this question, we need to first draw the picture. So here's the point where both cars started from. And going south is my green car at 50 miles per hour, and 50 miles per hour times 4 hours later, it's gone 200 miles. Now my blue car is going west, and it's going 40 miles per hour, and so after 4 hours it's traveled 160 miles. And we can use Pythagorean theorem to figure out the distance between the two cars after 4 hours, and that would be 256.12 miles when I round to 2 decimal places, and we'll label that length C. But we actually know more information. We know the green car is going 50 miles per hour, so that means the length of A is changing at a rate of 50 miles per hour. So I'll write that down. The derivative of A with respect to time is 50. And likewise for the blue car, that's going 40 miles per hour, so the rate of change of B with respect to time is 40. Now the question we were originally asked was, at what rate is the distance between the cars increasing 4 hours later? Well, using the notation in our picture, that'd be equivalent to asking, what is the derivative of C with respect to time? Well, to answer that, we need to know what equation relates all the information in our picture. Well, we're working with a right triangle, so that'd be a squared plus b squared is equal to c squared, right? The Pythagorean theorem. But I'm going to write this a little bit different, just to be explicit that a, b, and c are functions of time. And the reason I make note of that is because, well, the Pythagorean theorem alone is not good enough. I don't have a derivative of c with respect to time in the Pythagorean theorem, but notice if I took the derivative of c with respect to time, I would have. So what we're going to do is take the derivative of every single term. The reason why we do it to every single term is so that the equation still holds true. If you take the derivative of the right side, you take the derivative of the left side. But to take the derivative of every single term, we need to use chain rule on every term because there's a function within a function, right? Look at c of t. Well, c of t is a function. It's a function of time, and it's within another function. It's within the squaring function, right? It's being squared. So here we are using chain rule. There's the derivative of every single term. And there's a 2 common to every term, so we can get rid of the 2. And there we are. There's an equation involving all of our information. And the only thing that's unknown in that equation is what we want, the derivative of c with respect to t. So we're able to solve for that term. So the last step is plug in information. There we go. So we plugged in a and the derivative of a with respect to time, plugged in b and the derivative of b with respect to time, and the derivative of c with respect to time is unknown, but we can solve for it. And there we go. Solving for derivative of c with respect to time gives us 64.03 miles per hour. Now these 4 steps that we did are pretty important. It helped us break the problem into smaller pieces. We'll be doing a lot more related rates problems in class. But that's it for this video. Hopefully it has warmed you up for solving related rates problems in class.